In this question, we're going to look at section 6 of the 2018 exam for Math 121. All three parts are distinct, so we can answer each one of them separately. So, first off, find the quadratic Taylor polynomial approximation to the function f of x equals cos of 3x at the point x equals pi. And to do that, it helps to have the formula. In fact, it's essential to have the formula for a quadratic Taylor polynomial, which is f of a plus the slope f prime of a times x, but shifted by a, and then plus the second derivative over 2 times x minus a all squared. So that's our quadratic. Notice the x's only appear in the linear and quadratic terms here. Everything else is fixed at the point pi. So to be able to fill in the blanks in this formula, we need to know the function value. So let's just write this down here. And we also need the derivative, so we can calculate it. That'll be negative sine of 3x times 3, and then the second derivative will be negative the derivative of sine is cosine. We already have a 3, and then we'll get another 3 from the derivative again, and that will boil down to negative 9 cos of 3x. And then we evaluate that at the point we were asked for, which is x equals pi, or x equals pi for this. And so we're going to get f of pi is cos of 3 pi. We're going to get f prime of pi is negative sine, this is negative 3, sine of 3 pi, there's the 3. And the second derivative at pi is going to be negative 9 cos of 3 pi. Perfect. Now, no one wants to deal with these particular numbers. If we look in our calculator or look at a graph of cosine and sine, this is equal to negative 1. This is equal to 0, and this, well, cos of 3 pi is negative 1, so I'll have negative 9 times negative 1, which is positive 9. All right, putting those ingredients together, we now have the three function values, function, derivative, second derivative. A is pi everywhere, so we simply write out our Taylor polynomial of degree 2 as minus 1 plus 0, x minus pi, plus 9 over 2 x minus pi squared. And if you want, there's an optional tidying that we can do here, which is negative 1 plus 9 halves x minus pi squared. Just noting the 0 term does not play a role in the final answer. All right, part B and part C actually are both limit questions, totally separate. So let's dive in though. Looking at part C in advance, that's going to be something that requires L'Hopital's rule. So we'll try to do something different in B, though L'Hopital's rule will work just as well for part B as well, if that's what occurs to you. So here, the first thing I would do is assess what the limit is, just as a ballpark. And that just means subbing in this infinity here. And that's going to tend towards an infinitely large quantity in the top, but also an infinitely large one in the denominator. So that's one of our classic indeterminate forms. And if it's indeterminate, we have to go back to our starting point and see if we can do something with the original function before we take our limit. So because this is a polynomial over a polynomial, it actually is no problem whatsoever to simplify this into a nicer form, a more usable form for the limit. And that's simply to divide the numerator and denominator both by the same thing, here x cubed, the highest power that we see in our function. And of course, because we're doing that, we aren't changing the value, it's like multiplying by 1. What we see though is the payoff of turning some of these infinite quantities into finite ones. So we're gonna have 3 over x squared by the time we take 3x over x cubed. The minus 4x cubed though simply turns into the fixed quantity negative 4. Likewise, the 5x cubed turns into 5 minus 10 over x cubed. Now, the lovely part about that is that as x approaches infinity, 3 over x squared is going to be dividing by larger and larger numbers, heads towards 0. And negative 10 over x cubed is going to do the same thing. It's heading towards 0. So each of these terms in the numerator and denominator go away, but the negative 4 and 5 remain unchanged as x changes, and so we have our limit of negative 4/5. Now that same strategy will not work on part C, because here we had polynomials over polynomials. There was a highest power that we could use. However, in this expression, we have t's over lns, and that's not going to work because there's no power involved with ln of t. However, we still do see this indeterminate form. And fortunately, it's one of those forms that works perfectly for L'Hopital's rule, our other toolkit element. So we're going to take the same limit as t approaches infinity, but what L'Hopital's rule says is we can trade the original limit for the derivative of the numerator, 1, all divided by the derivative of the denominator, which is 1 over t. And then we just tidy that up a little bit. We get the limit as t approaches infinity of just t, 1 over t, and then that is very clearly going towards infinity, or the limit does not exist. There's no finite number that we're approaching as t approaches infinity here.